So what do we have if we have a transformation that's both injective and surjective simultaneously? Well, that's a very special case and a very important type of transformation, which we call a bijection or an isomorphism in the context of vector spaces. So let's start with the definition. So let T from V to W be a linear transformation. This linear transformation is a bijection, or again, an isomorphism. If T is injective, which is 1-to-1, and surjective, which is onto, right? We say T is an isomorphism between V and W. We say V and W are isomorphic, right? Denoted by V. A lot of the times, like this textbook uses just the squiggle here, but that's usually reserved for an equivalence relation. It turns out that isomorphism is an equivalence relation, and I would challenge you to prove that. But in general, usually we denote isomorphism with the equality, like this, the tilde over the equality here. And so I'm going to stick with this, although keep in mind that the book uses just the tilde for isomorphism. Okay. So what does this mean, right? This means a bijection T, and say this goes from V to W here. Right, this map of vector spaces. It's 1-to-1 and onto. So for a bijection, T is a bijection if the kernel of T is equal to 0 and the image of T is equal to W. This is a very nice classification of maps that are bijective, or that induce an isomorphism of vector spaces, right? You just check the kernel, see that the kernel has one element and it's the 0 element, or the additive identity of the domain. You check the image and see that it's the entire codomain, right? And so this is exactly maps which basically you can think about W as a copy of V, but represented differently, right? Because every element in V has a unique element that it's mapped to in W, and everything in W is mapped to, right? So it's 1-to-1 and onto. This is exactly the idea of a bijection or an isomorphism, right? It's basically, if you'd like to think about it in the context of vector spaces, it's the same space, but what you're calling elements of V and what you're calling elements of W are different, right? They're literally different in terms of whether it's a polynomial or a vector, but it's the same space, right? You can call it whatever you want. And in fact, so let's look here. Let's look at an example that maybe will make what I'm trying to say a little more clear here. Let's show that T from M2 to R4 is an isomorphism. Right? And so let me finish what I was saying here for a minute. So what this is saying is, as a space, the space of all 2x2 matrices is isomorphic to 4-dimensional Euclidean space. And what I'm saying is, whether you view elements of that as written like this or written like this, it doesn't matter. It's the same space, right? the same, it's the same properties, the same space, the same number of points, the same way the points behave, et cetera, right? It doesn't matter what you dress them up as, whether you dress them up as a 2x2 matrix or a 4x1 vector, right? It doesn't matter because it's the same space. And this is the idea of isomorphisms, is really it's just the same space being understood with different notation or in a different context. So how do we show such an isomorphism? Well, to show something is an isomorphism, for now, so let's write this out. To show a transformation is an isomorphism, we have to show the following things. We have to show that T is let's say a transformation T is a linear transformation. We have to show that it's injective, T is 1-to-1, and we have to show that T is surjective. If we can show all three of these things, then we've proven that the given map is an isomorphism. So I got a little bit carried away here. Let's describe explicitly what this map is doing. It's taking an element of M22 A, B, C, D, and the output is a vector A, B, C, D, like this, right? So let's prove that this is an isomorphism. Well, first we need to show, is T linear? What does it mean to show something's linear, right? Well, to show that a transformation is linear, we have to show that T of A V1 plus V2 is equal to A of T V1 plus B T V2, right? This is what we need to show. This is a want to show. So let's do that. Let's take, and let's not use A and B. Let's say here we want T of K times one element of the domain. So let's call that A1, B1, C1, D1 plus L, and then A2, B2, C2, D2, right? And we need to show that this is equal to K times T of A1, B1, C1, D1 plus L times T of A2, B2, right? So what is this? Well, this is T of KA1, KB1, KC1, KD1 plus LA2, LB2, LC2, LD2, right? Scaling the matrices inside of, like, we're scaling them in the domain before we map them to the image, right? This is equal to T of, we can also do matrix addition in the domain, which gives us K. So now this is T of, and it'll just be one matrix, K A1 plus L A2, K B1 plus L B2, K C1 plus L C2, and then K D1 plus L D2. Now, under the transformation, right, this takes the A11 entry to the first component of the vector, the A22 entry to the second, blah, 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 right? And so once we apply the transformation to this vector, or to this matrix, we're going to get a vector, which is AK1, sorry, what am I doing? KA1 plus LA2, KA2 plus B1, sorry, I got too many letters going on, it's alphabet soup. LB2, KC1 plus LC2, KD1 plus LD2. Now we can do our arithmetic in the codomain or in the image, right? Because we're in R4, which is also a vector space, which means we can split this vector up to KA1, KB1, KC1, KD1 plus LA2, LB2, LC2, D2, which is equal, we can scale. So K, A1, B1, C1, D1 plus L, A2, B2, C2, D2. But now this is equal to K times T of A1, B1, C1, D1 plus L times T of A2, B2, C2, D2, which shows that the linear property is held, right? Or that this is a linear transformation from M22 to R4, right? Because we've taken like T of K V1 plus L V2, and basically what we got was K T of V1 plus L T of V2. So we've shown that this is linear. How do we show that it's one-to-one? Well, let's to show that it's one-to-one, we need to look at, so that was linear. 2 is one-to-one, question mark, right? So here, this was T linear. And now I'm asking, is T one-to-one, question mark. What do I have to show that T is one-to-one? I have to show that T of A, B, C, D is equal to 0 implies that, well, and we can see this right away. This is pretty trivial, right? If T, A, B, C, D is equal to 0, 0, 0, 0, you can see by inspection that that implies A, B, C, D is equal to 0, 0, 0, 0, right? Cool. Then, to show, so that shows that T is onto, to show that, or one-to-one, to show that T is onto, this means we take an arbitrary X, Y, Z, W contained in R4. Does there exist a matrix that gets mapped to this? Well, then take M to be X, Y, Z, W. Then T of X, Y, Z, W is equal to X, Y, Z, W, which shows that it's onto. So we've shown that T is a linear transformation, that it's injective, and that it's surjective, which implies that T is an isomorphism. Moreover, this is shown that M22 is isomorphic to R4, right? And here's an exercise. Prove that MMN is isomorphic to R to the MN, right? We've proved that. We've done this exercise for M equals N equals 2. See if you can prove this in general. I've talked about this isomorphism before when I defined what the space of all M by N matrices is, but I want to see if you could, going through this kind of argument, see if you could prove this in general here. Okay. Remember, we also have the notions of composition and inverse. So let's recall these notions and then see how the theory of isomorphisms plays into this. So composition. Let's say we have a transformation T from V to W and then some other transformation S from W to capital Z. Then the composition is defined as, and we write it as S compose T, which is a map from V to Z, right? And if you, really what this is S compose T of a vector V is S of T of V, right? Really what you can think about is, you have your map T from V to W, you have your map S from W to Z, then you just take the composition, which is first T and then S, right? Okay, So that's composition. And then remember, we also have the notion of an inverse. We have for inverse, we have T. If T is a map from V to W, and S is some map from W to V, such that S compose T is equal to the identity on V, and T compose S is equal to the identity on W, then S, which we write as T inverse, is the inverse of T, right? And what does this mean here, right? This means like T of T inverse gives you the identity like 0 of W, and then T inverse of T gives you the identity of V. Okay, cool. Now that we've recalled what composition and inverse are, let's look at a proposition involving these. So here's a proposition. First, if T from V to W is an isomorphism, then this implies that T inverse from W to V is also an isomorphism. So we have that the inverse of an isomorphism or a bijection is also a bijection or isomorphism, right? We also have that if we have two isomorphisms, T from V to W and S from W to Z, these are isos, then this implies that S compose T from V to Z is an isomorphism. Okay, so we need to prove that the inverse of an isomorphism is an isomorphism and that the composition of isomorphic maps is also an isomorphism. So let's do that. Proof. And let's start with the inverse. So first, what do we need to do? We need to show, want to show that T inverse is linear. So 1, linear, 2, injective, 3, surjective, right? To show that T inverse is linear, we need to look at T inverse of a linear combination of elements in W, right? Because T inverse is a map from W to V. What are elements in W? Well, these are going to be of the form A T of so really this is going to be A of W1 plus B W2, right? But T itself is an isomorphism. So we can write this as T inverse A T of V1 plus B T of V2. This property really comes not from it being isomorphism, but more because it's a surjection, right? Because it's a surjection for every element in the domain or in the codomain W1, W2, there exists V1, V2 respectively, such that, right, that's the surjective property. Now, we also know that since T is an isomorphism, T is linear, which means we have T inverse and then T of A V1 plus B V2. That's the linear property of T because it's an isomorphism. Now, what is T inverse compose T? That's the identity on V. And so you get A V1 plus B V2. But V1, right, we can use the same notion of T inverse being the inverse to T and write this as A T inverse of T of V1 plus B T inverse T of V2, which is A T inverse of W1 plus B T inverse of W2, which shows that T inverse is, in fact, a linear transformation. Let's show that it's injective. Or surjective, it doesn't matter, right? Well, let's do injective first. Let's now show that T inverse is injective. So what we want to do is assume that T inverse of W is equal to 0. And we want to show that this implies, right? Well, what is W? Again, T itself is surjective because it's bijective. So this implies we have T inverse, like there exists some V such that W equals T of V, which equals 0, right? And so this implies that T of V equals 0. Or excuse me, this implies that V equals 0. But if V equals 0, then that implies that T of 0 equals 0, which implies that T inverse of 0 equals 0. This is a long-winded way of showing that W therefore must equal 0, right? Because this is true, V equals 0. That's only true if T of V equals 0, right? Because 0 maps to 0. So this implies that that we have an injection. Let's look at surjections. For all V in V, we have that V is equal to T inverse of T of V, which, so that immediately shows that T inverse is onto or surjective, right? Because for every element of the codomain, right? Because remember, T inverse is from W to V. So the codomain is V. And so for all V in V, we need an element W such that it's mapped to, right? And since T is equal to, or since V is equal to T inverse of T of V, then we found that element for every element in, right? So T of V gets mapped to V for all V in V. And so we've shown now that the inverse is a linear transformation, that it's one-to-one, and that it's onto. All right, let's do the same thing for composition. So let's look at S compose T of A V1 plus B V2. So we're showing, is the composition linear now, right? Is the composition linear? Well, I don't know. This is equal to S of T of A V1 plus B V2, which is equal to S of A T V1 plus B T V2, since T is an isomorphism, we have this linear transformation property, right? S is also an isomorphism, which means it also has a linear transformation property, which means this is A of S of T of V1 plus B of S of T of V2, which is equal to A S compose T of V1 plus B S compose T of V2, which shows that the composition is a linear transformation. Cool. We need to show that it's, I think I did surjective first for this one. So let's do surjective first. Now, S is a surjection implies for all. So remember, let's write up here. T is going from V to W, and then S is going from W to Z, right? S surjective means for all Z and Z, there exists a W in W such that Z equals S of W. And T surjective implies that for all W in W, there exists a V in V such that W equals T of V. Well, then putting these two surjective results together, we have that Z is equal to S of W, which is equal to S of T of V, which is S composed T of V. And this is for every Z there exists. So for all Z in Z, there exists V in V such that Z is equal to S composed T of V, which implies that S composed T is surjective. Cool. The last thing we need to show is injective, right? And to show that it's injective, what do we need to do? We need to look at S composed T of V equal to 0. And we need to show that if this is true, then V is equal to 0, right? So this means S of T of V is equal to 0, but S is injective. And if S is injective, that implies S of something equals to 0, means that something was also equal to 0, which this implies that T of V is equal to 0, since S is 1 to 1. But T is also 1 to 1, which implies T of something equals 0, means that something was equal to 0. So this implies Z is equal to 0 since T is 1 to 1. And so this implies that S composed T is 1 to 1. Therefore, S composed T is an isomorphism. And that would complete the proof showing that both the inverse of an isomorphic map is an isomorphism and the composition of two isomorphisms is an isomorphism. Now, with this theorem in mind, here's an exercise, a very important one that I'm not going to require it be done, but if we had more time in the semester, I think I would. Prove that isomorphism is an equivalence relation. Remember, what does that mean? I.e., show the relation isomorphism is reflexive, i.e., you need to show that a vector space is isomorphic to itself. You need to show that it's symmetric, i.e., if there's an isomorphism between V and W, that implies there's an isomorphism between W and V. And then third, show that it's transitive. Meaning if there's an isomorphism between V and W and an isomorphism between W and Z, not the integers, this implies that there's an isomorphism between V and Z, right? This is a very good exercise, and I think you would have the concepts of this lecture down a lot if you could prove this theorem or this relationship here. Okay. The last thing I want to do in discussion of isomorphisms is talk about what happens to basis elements. So theorem. T from V to W is an isomorphism if and only if when the collection of vectors V1 through Vn is a basis for V, the collection T of V1 through T of Vn is a basis for W. I.e., what does this mean? Right? This means that isomorphisms are exactly those transformations that take basis elements to basis elements. So isomorphisms are exactly those that take basis elements of V to basis elements of W, right? Those are what isomorphisms are. It's just redefining a basis of your space, right? So you have some basis of M22, you have an isomorphism that maps those basis elements to some other basis of R4, right? In the example that we were looking at. Let's look at an example. I claim that, well, I won't claim it because that would require proof. The showing it, like what we're doing is a proof really, but less formal. So let's show let's show that P2 is isomorphic to R3. So the space of all polynomials of degree less than or equal to 2 is actually just three-dimensional Euclidean space, or it's isomorphic to it. How could we show such an isomorphism exists, right? Well, by the previous theorem, we only have to show that there exists a linear transformation of basis elements to basis elements. So define T from P, well, let's do it from R3 to P2 by T of E1, right? What's a basis for R3? Well, the standard basis is E1, E2, E3, which is really I hat, J hat, K hat, right? And then the basis for P2 was 1x, x squared. So let's define T of E1 to be 1, T of E2 to be x, and then T of E3 to be x squared. This is a transformation that maps basis elements to basis elements uniquely. Therefore, it's an isomorphism by the previous theorem, which is pretty cool. i.e., we can explicitly describe the transformation from R3 to P2 of T of ABC is equal to AX squared plus BX plus C, right? This is an explicit isomorphism of R3 and P2. So here's a claim that I would like you to prove. Show that Pn is isomorphic to Rn plus 1. If you can do this, that's again, then I would argue you have a solid understanding of the course material as far. So show that the space of all polynomials of degree at most n is isomorphic to n plus 1 dimensional Euclidean space. All right, and you may notice here, what's the similarity here? Remember when we were talking about dimensions of vector spaces, we showed that the dimension of Pn is always n plus 1. Well, the dimension of Rn plus 1 is also n plus 1, right? So we have this theorem, and this will be my concluding theorem for today's lecture videos, that relates when things are isomorphic to the comparison of their dimensions. So we have a couple statements. We have that W or V is isomorphic to W if and only if their dimensions are the same. Okay, and so here, right, like the dimension of P2 is 3, the dimension of R3 is 3. They have the same dimension, that means they're isomorphic. What we did was found an explicit isomorphism between them. But we could have acknowledged that they are isomorphic without producing an explicit isomorphism had we had this theorem first that just said, look at the dimensions. Just count dimensions. If they're the same, you have an isomorphism. What else do we have here? We have if T from V to W is linear and the dimension of V is equal to the dimension of W, then the following are equivalent. T is 1-to-1 or injective. 2, T is onto or surjective. T is an isomorphism. Bijective. So if you have a linear transformation between two maps or between two vector spaces of the same dimension, if you can show they're injective, then you know it's a bijection. If you can show, like, so injections, surjections, bijections, they're all one and the same in the context of linear transformations from a vector space of a given dimension into another vector space of that same dimension, right? Because we know they have to be isomorphisms by part one of this theorem. Okay, so this wraps up what I wanted to say today, and it might have gone a little longer than I had planned, so I apologize if it got a little lengthy here. What we're going to do from here is tomorrow is the last day of new material, and we're going to wrap up the course with a little bit of talk about the kernel and image of a linear transformation. We've talked about it quite a bit, but let's focus primarily on the kernel and the image as subspaces of these vector spaces, which in turn makes them vector spaces themselves, right? And then after that, we'll talk a little bit about how you can represent linear transformations of arbitrary vector spaces as a matrix, right? And it may be a little different because it's not just between real valued vector spaces. There may be some more complicated stuff going on there. And that's what we'll explore tomorrow. And that will wrap up the course content for the semester. Thursday will be a final review, and then Friday will be the final exam itself.